Welcome to chapter 21 in physics. So this chapter is on circuits and DC instruments, and we'll be talking specifically about series circuits, parallel circuits, and combination series and parallel. All right, so let's start out with resistors wired in series. You have seen in class what a resistor looks like, and we've talked about series circuits as they relate to capacitors. Today, we'll look at a series circuit involving resistors. There are rules for this, just like there were rules for the capacitors circuits. So you can see, I want to make this just a tiny bit larger. All right, I think I like that better. You can see that our rules are that when you have the resistors, the individual resistors add to give you the total resistance. When you have currents in a series circuit, they're all equal. So the current that leaves the battery is the same as the current through the first resistor in the circuit will be the same as the current through the second resistor, and so on until you come back to the battery. The potentials, and remember that potential is just another name for the voltage. The potentials add. Sometimes we call these potentials the potential drop. Just two names for the same thing. So as you go around a series circuit, each individual component will experience a potential. And if you add them all up, they add up to the total. So the total potential, that would be the size of the battery, is equal to the individual potentials through each component in your circuit added together. And then finally, we have that the powers add. So the power used by the first resistor in the circuit plus the power used by the second and so on will add up to the total power in our circuit. All right, let's scroll down and see what we can do. Again, these are the rules for series circuits, and on a quiz, I'll provide them for you. So let's look at our series example. Whoops, oh, I see a problem already. They've got me in the middle of the words. I'll have to remember that. All right, so for the first example, we have a 10 ohm resistor and a 20 ohm resistor wired in series with a 300 volt battery. So this jagged line is the 10 ohm resistor. The second jagged line is the 20 ohm resistor. And these two lines, one long and one short, parallel to each other is the 300 volt battery. We know it's a series circuit because if you go from the battery, you go through the first resistor and then through the second and then back to the battery. There are no forks in the road. The current goes all the way around. So it's a series circuit. So it says find everything. Well, okay. We are going to start out usually with the total resistance. So we know that in series resistors add, so the total resistance is going to equal the resistance of the 10 ohm resistor plus the 20 ohm resistor. And you'll notice that on these subscripts, I've put a 10 instead of a 1 and a 2 or an A and a B. I usually use the size of the resistor. That way, I always remember which resistor I'm talking about. When I use 1 and 2 or A and B, I sometimes get myself confused. So 10 ohms plus 20 ohms gives you 30 ohms. We have 30 ohms for our total resistance in the circuit. To find the total potential, and again, remember potential is just voltage, that is just the size of the battery. So the total potential is 300 volts. It's the size of the battery. So we've had R and V, now we can find I. We can find the total current. So the total current we'll use Ohm's law. So V equals IR. V total equals I total multiplied by R total. So 300 volts will equal I total multiplied by 30 ohms To get rid of the 30 ohms on the right-hand side, you divide both sides by 30. So 300 volts divided by 10 ohms gives you a current of 10 amps. So we know our total current is 10 amps. Now we can find our total power. Power is equal to current times voltage. So P equals IV. P equals IV. So we know the total current is 10 amps. We know the total voltage is 300 volts. So 10 amps times 300 volts gives us 3,000 watts. And now we want to find out information about the individual components of the circuit. And to do that, I normally always start out with the resistance as a placekeeper, as a way to divide it up. So I'll always remember which resistor am I talking about. So if we look at the 10 ohm resistor, well, its resistance is 10 ohms. And then you can see the next step, I found the current through the 10 ohm resistor. Why didn't I find the voltage? Well, if you go back and you look at the rules, you'll find that the currents are all equal. And so I know the total current, it's 10 amps. If I know the total current, I know the current through the first resistor, through our 10 ohm resistor. So the current through the 10 ohm resistor is the same as the total current is equal to 10 amps. Now we can find the potential drop across the 10 ohm resistor, or the voltage of the 10 ohm resistor, or the potential of the 10 ohm resistor. Remember, we've got three ways to say this. So potential drop, or just potential, or just voltage for the 10 ohm resistor. And we would use Ohm's law. So V equals IR. That means that V10 equals I10 times R10. Well, we know the current through the 10 ohm resistor is 10 amps. We know the size of the 10 ohm resistor is 10 ohms. So 10 times 10 gives us 100 volts. If you took a voltmeter and put one side on the left of your 10 ohm resistor and one on the right side of the 10 ohm resistor, the voltmeter would show a reading of 100 volts. So now we can find the power. P equals IV, so P10 is I10 multiplied by V10. 10 amps times 100 volts is 1,000 watts. And now we can do these same things for the 20 ohm resistor. We can do the same things for the 20 ohm resistor. So we know that R20 is 20 ohms. We know that I20 is 10 amps because it's a series circuit and the currents are all equal in a series circuit. So I20 is equal to I total is equal to 10 amps. And now we can calculate V20. We can calculate the potential drop across the 20 ohm resistor, or another way to say that is we can calculate the voltage of the 20 ohm resistor, or the potential of the 20 ohm resistor. Again, three ways to say the same thing. So V equals IR, V20 is equal to I20 times R20. So 10 amps times 20 ohms is 200 volts. And you may remember, I don't normally like to do the math across the page. I like to do it vertically, but this was to save space and to get more views on a single frame in the video. Now to find P20, P equals IV. So P20 is I20 times V20. 10 amps times 200 volts gives you 2,000 watts. One thing you ought to notice that in the rules, the power adds. So the power used by the 10 ohm resistor and the power used by the 20 ohm resistor ought to add to give us the total power. And if you go back and look at our numbers, they do. P20 was 2,000 watts. P10 is 1,000 watts. So 1,000 plus 2,000 gives us 3,000 watts. And in fact, that is our total power. So you might go back and verify. And the same is true for the voltages, for the potential drops. They add. So P10 was 100 volts, P20, I'm sorry, not P. V10 was 100 volts. V20 was 200 volts, and 100 plus 200 gives us 300 volts, and that's the size of the battery. All right, for practice, you can do this circuit with 3 resistors wired in series. And you can also do the ones on the study guide. And again, as always, if you need help, please ask for it. All right, we are going to look at resistors in parallel. I'm going to look at resistors in parallel. So resistors in parallel, there is a fork in the road. Our circuit is such that when the current leaves the battery, as it moves around, it has to split to go through the components. So this first drawing, we have 2 resistors wired in parallel, and then they come back together and go back to the battery. On this one, we come from the battery and we have 1, 2, 3 paths before they reconnect and come back. So you can have any number of resistors wired in parallel. There are rules for this. You'll be given the rules on the test. So the resistance adds as the inverse. That means that 1 over R1 plus 1 over R2 plus and so on gives you 1 over R total. Once you have 1 over R total, you can invert that to find just R total. The currents add. The currents add. So we know that I1 plus I2 plus and so on will give us I total. The potentials are all equal. V total equals V1 equals V2 and so on. And the powers add. P1 plus P2 plus and so on will give us P total. So as our example, we have a 300 volt battery wired to a circuit where we have a 5 ohm and a 10 ohm resistor wired in parallel. One thing you ought to notice as we go along, current takes the path of least resistance. So as we do this, we would expect to have the larger current passing through the 5 ohm resistor than we would through the 10 ohm resistor. So we'll just see if it works out that way. All right, always start out finding the total. So 1 over R total equals 1 over R5 plus 1 over R10. So, and again, I probably shouldn't have written them on a single line. I probably should have made it 1 and a horizontal line and R total underneath it. I'm always worried when you use this little diagonal slash that you'll make a mistake. So just be careful. So 1 over R total is 1 over 5 ohms plus 1 over 10 ohms, but 1 over 5 is 0.2 and 1 over 10 is 0.1. So 0.2 plus 0.1 is 0.3. And we're not finished. R total has to be 1 divided by 0.3, which gives us 3.33 ohms. 3.33 ohms. V total will be the size of the battery. So that's 300 volts. And we can calculate I total. To do that, we use Ohm's law. So V equals IR. V equals IR. So we write down V equals IR. I went ahead and said, okay, I'm solving for I. Let's divide both sides by R. You could have plugged in the numbers and then done the math. It's up to you. So V is 300 volts, R is 3.33 ohms. So 300 divided by 3.33 gives us 90 amps. And then finally, we can find P total. P equals IV, so P total equals I total times V total. 90 amps times 300 volts, which gives us 27,000 watts. And now we can do these same things for the 5 ohm resistor. Because you remember, I predicted that the 5 ohm resistor will have the larger current because electricity takes the path of least resistance. So let's divide it all, separate it out into parts. So R5 is 5 ohms. If you look back at the rules, the voltages are all equal for a parallel circuit. So V5 will equal V total will equal 300 volts. And that means we can use the formula V equals IR to calculate I. To calculate I, we'll use the formula. So V equals IR, that means that I will equal V divided by R. So 300 volts divided by 5 ohms is 60 amps. And then we can calculate the power, P equals IV. So 60 amps times 300 volts is 18,000 watts. If we look at the 10 ohm resistor, its resistance is 10 ohms. Its potential drop or voltage or electric potential is the same as the total. It's 300 volts. We can use V equals IR to calculate I. I will be V divided by R. So 300 volts divided by 10 ohms, which gives us 30 amps. And you can see I was right. The 5 ohm resistor had a much larger current flowing through it than the 10 ohm resistor did. In fact, you'll notice that it's twice as big because the size of the resistor is half the size of the other one. All right, P10 would be I10 times V10, so 300 amps times 300 volts would give you 9,000 watts. And you also ought to notice that since the powers add, 18,000 watts plus 9,000 watts gives you 27,000 watts, which was P total. All right. So for practice, you can do this circuit with the 3 resistors in it and also the ones in the study guide. The ones in the study guide. And again, I'll give you the formulas for series and parallel circuits, but I promise you, you still need to practice or you won't know what you're doing. Okay, now for the hard part. We're gonna put it all together. So sometimes circuits are not all series or all parallel, they're a combination. And in a combination, each part follows its own rules. So let's look at our combination circuit. Oftentimes they're drawn in an odd way where you can't really tell what's series and what's parallel. So you can see I have 5 resistors wired to a 1000 volt power supply. The first thing I usually tell people to do is to redraw the circuit so that it looks like a series parallel combination. And you can see I've done that for you, but let's trace it out. So we always start at the battery. And then if you'll notice on the one you're given, you start at the battery and we come up to the first resistor. So here I've started at the battery, I've come up to the first resistor. After you pass through that first resistor, the 5 ohm resistor, you'll see there's a fork in the road. We have to split. So I have drawn in the split. We leave the 5 ohm resistor and then we split. And I've chosen to do the top part of it first. So we hit a 10 ohm resistor followed by a 40 ohm resistor before there's another fork in the road. So I've gone to the top part. Here's the 10 ohm and the 40 ohm. And here is the part where we come back together. So we've drawn in the battery, the 5 ohm resistor, and the top part of the split. Let's go back to the 5 ohm resistor and come down and do the lower part. So you can see we hit a 20 ohm resistor, which I've drawn in, but then we hit a split. So 20 ohm resistor and we hit a split. And you see that that's where the 40 and the 20 come back together. And that's what this is. And then finally we go from here to the 15 ohm resistor. So we go to the 15 ohm resistor and then it's a simple path back to the battery. You have to be able to take a circuit that looks like this top diagram and turn it into something that looks like the bottom diagram. And I will try to remember in lab to give us some practice ones to do. All right, so after we've done this, after we have a more simplified version that looks like series and parallel, because you can see these two are in series, but the top line and the bottom line are in parallel. And it looks like a combination. So what you do is you look at the most complex part. So we go inside the parallel part and notice that these two are more complex than the bottom. So we'll start with this, the 10 and the 40 ohm resistor. You can see by looking at them that they're wired in series, and you know how to handle that. So when they're wired in series, they add. So R10 plus R40 gives you R50. And as soon as we've done that, we take our diagram and we redraw it. Instead of a 10 and the 40 on the top branch, now we have a single 50 ohm resistor. All right, and now we look at the most complex part of it. So you can see that the most complex part of it would be this parallel part. So we need to look at the 50, 20 ohm parallel section and come up with our values. So the 50 and the 20 ohm, it's in parallel. So 1 over R total is equal to 1 over R1 plus 1 over R2. So 1 over 50 plus 1 over 20. But 1 over 50 is 0.02 and 1 over 20 is 0.05. You add them up, you get 0.07. We're not done yet. We don't want 1 over R total. We want R total. So I have to take 1 over 0.07 in order to get our total, and it gives me a value of 14.29 ohms. So now we redraw our circuit again, but we ditch the parallel part and replace it with a single resistor valued at 14.29 ohms. Oh, and I went too far. I apologize. Okay, so now it looks like this. The battery, the 5 ohm resistor, this 14.29 ohms replaces the parallel part. This is referred to as the equivalent circuit. It's equal to that very first one. Now we see it's a simple series circuit. So R total equals R1 plus R2 plus R3. So 5 ohms plus 14.29 ohms plus 15 ohms. And that gives us a total of 34.29 ohms. That's our total. So now that we have our total, it's easy enough to find V total. That's just the size of the battery. So 1,000 volts. And once you have V and R, you can calculate I. So V equals IR. That means 1,000 volts will equal I total multiplied by that 34.29 ohms. Divide both sides by the 34.29 and you get that I total is 29.16 amps. And now we can find P total. P equals IV, so P total is 29.16 amps times the 1,000 volts, which gives us 29,160 watts. Okay, for practice, you should work on this one and the problems on the study guide. And we will stop here. Oops, if I can type. And pick up with the rest of it in video 2. So I will stop my share and I will stop the recording.